Hey, good evening. Um, First of all, I just want to say it was a pleasure meeting all of you at the ICEAP meeting, and I really appreciated everyone's questions, and I apologize for not being able to get back with you the following day with a more detailed answer. So what I thought I'd do is I'd create this YouTube video explaining a little bit about paleomagnetism. And you are welcome to leave questions in the YouTube uh, app at whatever time, and I'll be happy to answer them. So I just want to go through some very simple things. And first of all, the collection, how we collect samples. And we drill them in a field with a gasoline powered drill, and then they are oriented. So when we extract the samples, we want to know exactly the angle and the direction that we drilled those samples. We have to have that information. So then we take the sample back to the lab and we will analyze the sample in a magnetometer, and we will get two pieces of information from that rock sample. And the first piece of information we will get is declination. And declination is the compass that everyone is familiar with, right? The compass is always north seeking, at least in the present day. And so when a rock forms, a sedimentary rock or an igneous rock, the magnetic minerals in that rock will align themselves with the North Pole, in this case, the North Magnetic Pole. But we consider that the North Magnetic Pole over time averages to the geographic North Pole. So when that rock forms and the Earth's magnetic field is the same way it is today, then it will have a declination of 360 degrees. If the pole is instead south seeking or reversed, as it was 780,000 years ago, then that sample will have a declination of exactly 180 degrees. So that's the only two directions that will be recorded in the rock when it forms, either 360 or 180. But if the continent moves after it's recorded, of course, when we measure it, it's not going to point to north because that rock will be moved and rotated along with the continent that it's resting on. I'll show you an example of this in just a minute. The second piece of information we get is something called inclination. This is the angle that the vector magnetic field makes with the Earth's surface. And it varies according to latitude by a simple formula, in that the tangent of the inclination is equal to 2 times the tangent of the latitude. So at the equator, the inclination is 0, and at the pole, the inclination is 90. And in between the equator and the pole, it will vary according to this formula. Those are the two key pieces of information that we need in order to reconstruct continents in the past. Okay, so here's some pictures. Here's a picture of me drilling in the field with Dr. Manoj Pandit from U of Rajasthan and Dr. Anup Sinha, who is with the with the government organization in the magnetic field up in Varanasi. So we'll drill the sample, and then we'll use this orienting tool right here, a very handy orientation tool. And this has, you can see, or maybe you can't, but it has markings that go from 0 to up above 90. But basically, we generally either drill vertically or horizontally or somewhere in between. And this will tell us the angle that we drilled at. And we have a Breton compass that fits in here, and it will tell us the direction that we drilled. And we'll make a little tick mark. It's hard to see here, but we'll make a little marking on the core that tells us which direction we drilled before we take it out. And then we'll remove the sample, and this is what it looks like. And I have a sample here. I'll hold it up to the camera So you can see, and you can see that I've marked it with arrows. The arrows point towards the bottom of the core, and you can see on the top, there's a little marking here, and that little marking there tells me which direction I drilled. And I'll record that in my field book along with the sample number. And you can see the sample number is written here. In this case, it's I244-1. So this sample happens to be from the Bander Formation. I think we took this one near Bundi. So this, we'll take this back to lab and we'll cut it into probably 3 different pieces, and then we'll measure that in the lab. Okay, so now we turn to, all right, we've measured the sample and we get an answer. And suppose that after we measure a bunch of samples, we get an average declination 335, and we get an average inclination of 66. Well, how do we take this information and then position the continent according to this information? Well, the first thing we do is we know where we sampled, and we assume that where we sampled, so I sampled from the Upper Vindian, from the Bander Formation, and I assuming that that was part of the North India block or the Bundelkhand Craton. So how can I restore the Bundelkhand Craton to where it was located when these rocks formed? I can do this for any place in India. So I'm just going to use it as an illustration. I'll just use one end of the arrow to represent the sampling location. I'll show you how we restore it. So suppose that this is how we found, this is at the end of this arrow, this is where we sampled, and we have a declination 335. So we can see it's not pointing towards the North Pole, right? It's pointing at an angle to the North Pole. And the inclination is 66 degrees. Well, I already told you when this rock formed, we know that it was pointing towards the North Pole. So the first thing we have to do is we have to rotate the continent and rotate this so that our arrow now points towards the North Pole. So when we do that, now we can see our arrow is pointing towards the North Pole. So what we've done here is we've taken our measured declination and we said, okay, we need to rotate India so that it's facing the North Pole. Okay, this is an imaginary scenario. So this is not a real scenario. I just want to point that out. But what I've done is I've got our measurement and I say, wait a minute, first thing I need to do, that's not pointing towards geographic north. I need to rotate it so it points geographic north. And that's what I've done here. The second piece of information we get is inclination. And inclination gives us the latitude at which the rock formed. So the rock here, this is where we collected it and then reoriented it. We can see it's about, let's say, 25 degrees north. Well, we have to actually figure out where it was according to the inclination. The inclination was 66. So we use our little formula and we find out that the rock was actually formed at 48.3 degrees north. So we have it pointing towards the North Geographic Pole, but we have it at the wrong latitude. So what we need to do is move it to the correct latitude. And that's what I've done here. And now our little spot is in the correct latitude and in the correct orientation. And what we've done is we've taken a sample, we made our measurements, and now we put India to the position it was located at the time our hypothetical rock formed. So here's kind of the steps that we went through. All right, this is what we found. We took our sample, we went back to the lab, we made our measurements, and we found out, hey, it's pointing not north. But we know when the rock formed, it had to be pointing north. So the first thing we do is we rotate our continent back so that our magnetic direction is facing geographic north. Then we use our inclination to position it according to the proper latitude. All right. And that is how we take that information from the rock, the declination and inclination, and use it to reconstruct continents in the past. Now there's one caveat, at least one caveat to all this. Notice that I've put India so that our arrow is pointing towards the North Pole, and I have it at the right latitude. But guess what? This is correct, but this one's correct too, because it's pointing towards the North Pole. It's at the right latitude. This one is also correct because it's pointing to the North Pole and it's at the right latitude. So one of the problems with paleomagnetic data is that we can position the continent in terms of what it was, how it was oriented, which way it was facing, and we can position the continent according to latitude, but we have no control on the longitude. The longitude can be anything as long as our arrow is pointing north and our site is at the correct latitude, okay? So that means we have to use additional information in order to position any continent according to some relative paleolongitude. We don't know paleolongitude. But let's say we have dinosaur tracks that lead from South America into Africa. Well, we know that dinosaurs didn't swim across the Atlantic and then get up on the other shore and walk there. But if we connect South America and Africa so that our trackways line up, then we know we positioned it in the correct relative longitude. We can move it anywhere, but at least we know that South America and Africa were together, because after we correct for their orientation and their latitude, they fit together nicely, and that trackway goes right from South America into Africa. All right. One of the issues that paleomagnetists have to deal with is that if we're dealing with a number of paleomagnetic poles and we want to trace, say, India's motion for the last 50 million years, and this is a hypothetical situation. These are not real data, but they're used to illustrate my point. We can draw India at 50, at 45, at 40, at 35, at 30, at 25, at 20, at 15, and 10, and so forth. We can make a little map of India at each one of those time periods. But from a graphical standpoint, that's all. This is just a graphical, illustrative concept that paleomagnetists came up with. Instead of plotting the motion of the continent, we plot the artificial or the apparent motion of the paleomagnetic pole. And this is confusing, and I understand it's confusing, but I'm hoping that through this short video, I can explain it to you. And it's simply this. Each one of these is a paleomagnetic pole, and it's calculated based on where we collected the sample, what direction the declination and inclination point. And we can use that paleomagnetic pole to reconstruct the entire continent. And the way we do that is we simply attach the pole to the continent and move it to north, move the paleomagnetic pole to geographic north or geographic south, because the paleomagnetic pole represents the geographic North Pole. Even though it's not plotted there, it may be plotted somewhere else. In order to reconstruct the continent, we simply move the pole. I showed you how to do it using declination and inclination. This is just another way to position the continent. So let's go through this. And the key thing here to remember is the paleomagnetic pole is the geographic North or South Pole. They are the same thing. So when we look at a paleomagnetic pole at 50 million years ago, and that paleomagnetic pole is sitting right in north central India, that tells me as a paleomagnetist that north central India was very close. Well, actually, it was exactly at the geographic North Pole. So in order to reconstruct India at 50 million years ago, I just attach this to India and slide it all the way up to the North Pole, and then I've reconstructed India. So let's go through this. All right. So all I've done is I've moved this right up to the North Pole, and that is where India was located 50 million years ago in this imaginary scenario. This is not really where India was 50 million years ago. This is illustrative to show you. Now, when I look at there, I see that the pole, the apparent pole, is moving away from India. And what that means is that India is moving away from the geographic North Pole. So at 40 million years, we can see that India has moved away from the pole because the paleomagnetic pole, which represents the geographic pole, has moved away from India. At 30, it's moved even further away from the pole because we can see the distance from where this point in India is located to where the paleomagnetic pole is now this distance from geographic north. We can do it again at 20 million years and at 10 million years. So this is just a convenience, and it's convenience so that we don't have to plot 1, 2, 3, 4, 5 Indias. We only have to plot India once and the poles 5 times. It's just a matter of convenience, and it's confusing, but remember, the closer the paleomagnetic pole is to the continent, the closer the continent is to the geographic pole. All right. Now, let's go through one more illustration because I've shown you one where the continent is just moving to the north and it's not rotating at all. Okay. But a paleomagnetic pole will also tell us about the rotation and the latitudinal change. So here I've made a scenario where I have paleomagnetic poles at 30, 20, 10, and 0. And I'm just showing you, I've attached these to India. And I've moved the 30 million year old paleomagnetic pole up to geographic north. And this is where India would have been 30 million years ago in this hypothetical scenario. So in order to position India at 20, I'm going to keep it attached to India right here, and I'm going to move this up to the geographic North Pole. And now you see I've reconstructed India 20 million years ago. I can do the same thing for 10 and for 0. Okay, all I'm doing is I'm taking each of those paleomagnetic poles, attaching them to India, and then moving India to its location. It's that simple. All right. Let's turn from apparent polar wander, which is what I just showed you, where it appears that the paleomagnetic pole is moving when in fact it's the continent that's moving, to something called true polar wander. And in true polar wander, all of the continents, all of the oceans move in unison in the same direction at the same speed over the same time interval. And this happens because the Earth wants to maintain a balanced spin axis. And we call the spin axis the maximum moment of inertia. And there are 3 moments of inertia for the planet: the maximum, the intermediate, and the minimum axis. And those have an orthogonal relationship to one another. They're each oriented 90 degrees away from one another. The spin axis is the maximum moment of inertia for the planet because it's spinning about that axis. Located 90 degrees away from the spin axis will be the minimum moment of inertia. And then 90 degrees away from the minimum moment of inertia will be the intermediate moment of inertia. What happens inside the Earth is we know that the Earth's mantle is dynamic. We know the surface is dynamic. And we know that plumes rise up from the core mantle boundary and that slabs sink down as they subduct towards the core mantle boundary. Slabs, because of their density, they're negatively buoyant, sinking towards the core mantle boundary. When we put those into the upper mantle, they create a mass excess, too much mass in the upper mantle. And the Earth feels that, and it gets a little bit out of balance. So what it does is it takes the entire mantle plus lithosphere plus crust, and it tries to move that mass towards the equator when those slabs are in the upper mantle. Now, as the slabs transition into the lower mantle, now, in order to maintain its balance, the Earth tries to move everything back towards the pole. All right. Kind of the opposite things happen when we release a plume from the core mantle boundary. A plume is less dense, and therefore, in the lower mantle, we have a mass deficit in the lower mantle. And this tends to shift the plumes towards the equator. And as they move into the upper mantle, now we have a mass deficit in the upper mantle, and we try to shift those back towards the pole. So this is an oscillatory motion. Depending on where the plume is, the Earth will adjust, or where the slab is, the Earth will adjust accordingly. So I've shown in this illustration here a mass excess, a slab sinking towards the core mantle boundary at mid-latitudes. And we can see that the Earth will try to shift that towards the equator, whereas with a plume coming up from the core mantle boundary, we'll also see in this case that the plumes will be shifted towards the equator, and then the opposite will occur, in depending on where the plume and the mantle are. So that's true polar wander. So in true polar wander, I've shown the minimum axis of inertia and the maximum moment of inertia. And 90 degrees away from this, 30, 60, 90, the intermediate axis of inertia will be located right here. Now, in true polar wander, we can imagine that we have three Indias. We'll just use India, but this can be three continents. One continent is located, our site is located right smack dab in that continent. And in our other, it's 90 degrees away from I min, right at I max. So let's track the motion of these three continents during true polar wander. All right. And in this case, remember, we're trying to move the slabs towards the equator. So what you will notice is that in the case of the site located right at the minimum moment of inertia, there will be absolutely no change in latitude during true polar wander, but it will spin, it will rotate. At the maximum moment of inertia, because it's 90 degrees away from I min, it will move only latitudinally. It will have no rotational motion. And a continent located somewhere in between will have some combination of rotation plus latitudinal change. So the closer you are to I min, the more rotational change you will see. The closer to I max, the more latitudinal motion you will see. So I can show you this. And what happens is we're going to push these continents towards the equator. And in doing so, we're going to maintain the spin axis. The spin axis is not going to change, but I'm going to use the ancient location of the spin axis to kind of mimic this motion. So here we can see the initial rotation. Notice that the spot on the yellow continent has only rotated. It has not moved latitudinally. The same spot on this green continent has moved latitudinally and rotated. And the same spot on this blue continent has only moved latitudinally. So here is the old spin axis, and the new spin axis has stayed right where it was. But notice that the entire outer surface, so we can imagine that this is the core mantle, or the mantle, lithosphere, and crust has all moved, and it's all moved this distance. And this is just a reference point showing where the old spin axis was. The spin axis never moves, but that reference location to where it was has moved. We can go another step and another step, and we can see, again, our spot here at I min has only rotated. This one has both rotated and moved latitudinally, and this one has only moved latitudinally. and then we can move it one more. And in this case, what's happened is the spin axis always stays the same. But notice that our reference point of where the spin axis used to be, the spin axis used to be here, and it has been moved towards the equator because of that mass excess. And notice we maintain, so this has now become, our I max has now become our I intermediate. And so we've switched these inertial axes. That's what true polar wander. True polar wander is different. Everything on the Earth moves in the same direction, at the same speed, in the same time interval. But some of that speed may be rotational, and some of it may be latitudinal, or some of it may be only latitudinal and only rotational, but it will always be the same. So in this case, because I made it an ideal case, everything is going to move 90 degrees over some interval of time. This spot on the yellow will only have rotated a certain number of degrees in a certain amount of the same amount of time. This one will have both rotated and had latitudinal motion, and this one will have only latitudinal motion. So hopefully that explains a little bit better true polar wander and apparent polar wander. And I'm happy to answer any questions that you might post below this YouTube video. And thanks for the questions. They were really good questions, and I really wanted to give you a more detailed answer. So I hope you enjoy this, and I'm happy to answer any further questions.